Look up at the night sky. What do you see? A vast, endless ocean of darkness, speckled with tiny pinpricks of light. But each of those distant gleams isn't just a star. It's an entire galaxy, a swirling metropolis of billions upon billions of stars, planets, and cosmic wonders. And here's the mind-bending part. Every single one of those galaxies has a story, a dramatic, violent, beautiful saga of birth, transformation, and sometimes even destruction. How did these glittering islands of stars come to be? What cosmic forces shaped their dazzling spirals, their blazing cores, their delicate dance through the darkness? The answers are stranger and more awe-inspiring than fiction. For centuries, humans have gazed at the heavens, searching for clues to unravel the mysteries of galaxy formation and evolution. And today, thanks to cutting-edge telescopes and brilliant scientific minds, we're piecing together the puzzle like never before. Did you know that some galaxies are nearly as old as the universe itself? That others collide in spectacular, slow-motion dances lasting billions of years, that hidden giant supermassive black holes lurk at their hearts, shaping their destiny. Over the next few minutes, we'll take you on a journey through 30 of the most astonishing facts about how galaxies form, evolve, and sometimes vanish into the cosmic shadows. This isn't just a story about distant lights in the sky, it's a story about us. The atoms in your body were forged in the hearts of stars, scattered across the cosmos by exploding supernova, and woven into new solar systems by the very forces we're about to explore. So buckle up, we're diving deep into the cosmic tapestry where gravity sculpts giants, dark matter weaves invisible webs, and newborn stars ignite like fireworks across the void. By the time we're done, you'll never look at the night sky the same way again. Think of the universe just moments after the Big Bang, an unimaginably hot, dense soup of particles so tightly packed that light itself couldn't escape. But hidden in that chaos were tiny ripples, quantum fluctuations no bigger than a fraction of an atom. These microscopic wrinkles in space-time would one day grow into galaxies, though at the time they were utterly insignificant. So how did these faint imperfections become the titanic structures we see today? The secret lies in a phenomenon called cosmic inflation, a blink and you'd miss it moment when the universe expanded faster than the speed of light, stretching those tiny quantum ripples into vast cosmic mountains and valleys. Gravity did the rest. Where the early universe was slightly denser, matter began to clump together, pulling in more gas and particles over billions of years. Picture it like a slow-motion avalanche, tiny snowflakes accumulating until they become an unstoppable force. Those initial over-dense regions became the nurseries of the first galaxies, drawing in swirling clouds of hydrogen and helium, the cosmic building blocks of stars. And here's the astonishing part. The patterns we see in today's universe, the sprawling galaxy clusters, the delicate filaments of the cosmic web, trace their origins directly back to those quantum ripples. Even now, telescopes like the James Webb Space Telescope are peering back to the universe's earliest epochs, capturing light from galaxies so distant they existed just a few 100 million years after the Big Bang. These ancient galaxies shouldn't have had time to form, yet there they are, proof that the seeds of cosmic structure were planted far earlier than we once thought. Every galaxy, from the smallest dwarf to the largest supercluster, carries the imprint of that primordial chaos, a cosmic fingerprint from the dawn of time. In the cosmic dark, something unseen holds galaxies together, an invisible force so powerful it dictates the very architecture of the universe. We're talking about dark matter, the mysterious substance that makes up roughly 27% of the cosmos, yet refuses to interact with light. Without it, galaxies as we know them simply wouldn't exist. Think of dark matter as the hidden scaffolding of the universe, an enormous cosmic skeleton whose gravity sculpted the first galaxies and continues to shape their evolution today. Early in the universe's history, ordinary matter, the stuff that makes up stars, planets, and us, was too hot and energetic to clump together efficiently. But dark matter, unaffected by the searing heat, began collapsing under its own gravity, forming vast web-like structures stretching across the cosmos. These filaments acted like cosmic highways, funneling gas into dense nodes where galaxies would eventually ignite. Supercomputer simulations reveal this stunning process in action, showing dark matter's gravitational pull drawing matter into intricate patterns resembling a spider's web. Where these filaments intersect, galaxies cluster like glittering cities at the crossroads of invisible highways. Some of the most compelling evidence comes from gravitational lensing, where the gravity of dark matter bends light from distant galaxies, warping their images into eerie arcs and rings. This phenomenon lets astronomers map dark matter's distribution, revealing its ghostly fingerprints on the universe. And here's what's truly wild: without dark matter's gravitational glue, galaxies would spin themselves apart. Stars on the outer edges of spiral galaxies move far faster than visible matter alone can explain, proof that an unseen halo of dark matter surrounds them, anchoring them in place. The cosmic web isn't static, it's a dynamic, evolving structure. Even now, dark matter's pull guides galaxies into colossal clusters, some containing thousands of members, while others drift in isolated voids. This grand architecture, built by an invisible hand, determines where stars will shine and where darkness will linger. Every galaxy, from the tiniest dwarf to the grandest spiral, owes its existence to the silent, unyielding grip of dark matter. Hidden in the vast cosmic expanse are ancient relics, galaxies so small and faint they'd be invisible to the naked eye, yet they hold secrets dating back to the dawn of time. Meet the ultra-faint dwarf galaxies like Segway 1, cosmic time capsules barely 1,000th the size of our Milky Way, but brimming with stars nearly as old as the universe itself. These tiny titans formed over 13 billion years ago when the cosmos was still in its infancy, and they've barely changed since. While their unassuming appearance might make them easy to overlook, their importance is monumental. They're the living fossils of galactic evolution, offering us a pristine window into the universe's earliest chapters. What makes these dwarf galaxies so special? Their stars are among the first ever born, forged from the pure, primordial hydrogen and helium left behind by the Big Bang. Unlike younger galaxies, which recycle material through generations of stars, these tiny systems are cosmic museums, preserving the chemical fingerprints of the early universe. Their stars contain almost none of the heavier elements like carbon, oxygen, or iron that define modern stars and planets. That scarcity tells a story. These galaxies formed before the universe had time to cook up complex elements in the furnaces of supernova. Studying them is like sifting through the ashes of the first cosmic fires, uncovering clues about how the earliest structures took shape, but their small size is deceptive. Despite their modest stature, these dwarfs played a colossal role in shaping the universe we see today. Computer simulations suggest they were the building blocks of larger galaxies, merging over eons through gravity's relentless pull. Think of them as cosmic bricks, small and unremarkable alone, but essential in constructing the grand cathedrals of modern galaxy clusters. Even now, their descendants orbit giants like the Milky Way, their ancient stars testifying to a time when the universe was young, chaotic, and brimming with possibility. The discovery of ultra-faint dwarfs has revolutionized galactic archaeology, turning faint smudges on telescope images into priceless records of cosmic history. Each one is a puzzle piece, helping us understand how the first galaxies ignited, how dark matter shaped their growth, and why some survived virtually unchanged while others evolved into the spirals and ellipticals we recognize today. They remind us that in the grand tapestry of the cosmos, even the smallest threads can weave the most extraordinary tales. The Milky Way seems peaceful when we gaze at its shimmering band across the night sky, but don't let its serenity fool you. Our galaxy is a cosmic predator, one that grew to its enormous size by consuming smaller galaxies in violent mergers. This process, called galactic cannibalism, isn't unique to the Milky Way. Across the universe, massive galaxies grow by tearing apart and absorbing their smaller neighbors, leaving behind ghostly trails of stars as evidence of their feasts. One of the most dramatic examples was discovered by the Gaia Space Telescope, a shattered dwarf galaxy nicknamed the Sausage Galaxy for its stretched, elongated remains. Around 8 to 10 billion years ago, this ill-fated galaxy collided with the young Milky Way, and gravity did the rest. The smaller galaxy was ripped apart, its stars scattered into looping streams that still orbit our galactic core today. These stellar rivers, invisible to the naked eye but detectable through precise telescope measurements, trace the path of an ancient cataclysm. They're like cosmic breadcrumbs revealing the Milky Way's violent past. But this wasn't a one-time event. The Milky Way's halo, a vast, diffuse cloud of stars surrounding its main disk, is littered with similar remnants of past mergers. Some, like the Sagittarius dwarf galaxy, are still in the process of being torn apart, their stars slowly being assimilated into our galaxy's structure. Others are so thoroughly digested that only subtle chemical signatures in starlight betray their origins. Each merger leaves a distinct imprint, like a chef recognizing ingredients in a blended dish. Stars from devoured galaxies often have different ages, compositions, and orbital paths compared to native Milky Way stars, allowing astronomers to reconstruct these cosmic meals billions of years after they occurred. The process isn't just destructive, it's transformative. When galaxies merge, their gas clouds collide, triggering bursts of new star formation. The influx of fresh material can rejuvenate aging galaxies, staving off their eventual decline. Even our solar system might owe its existence to one of these ancient mergers, as the shock waves from a galactic collision could have compressed gas clouds, igniting the star that became our sun. Galactic cannibalism isn't just a quirk of our corner of the universe, it's a fundamental driver of galactic evolution. Some of the most massive galaxies we see today, like the giant ellipticals at the hearts of galaxy clusters, likely grew by consuming dozens of smaller systems over billions of years. Their smooth, featureless shapes betray violent pasts, the result of so many mergers that any original structure has been erased. Meanwhile, spiral galaxies like the Milky Way merge more carefully, preserving their delicate disks while still growing through strategic acquisitions. The next time you look up at the Milky Way, remember, you're staring at a cosmic graveyard, one where the bones of devoured galaxies still swirl silently in the darkness. Their sacrifice built the galaxy we call home, and their legacy lives on in every star, planet, and even in us. After all, without these ancient mergers, the Milky Way and Earth might never have existed at all. At the heart of nearly every massive galaxy, including our own Milky Way, lurks a monster, a supermassive black hole with gravity so fierce it warps space-time itself. These cosmic behemoths aren't just passive inhabitants, they're active architects shaping their host galaxies in ways we're only beginning to understand. The relationship between a galaxy and its central black hole is one of the most fascinating and violent symbioses in the universe. They grow together, feed together, and sometimes the black hole even puts the brakes on the galaxy's future. Take quasars, for example, the brightest objects in the universe. These are supermassive black holes in their most ravenous phase, devouring gas and dust at staggering rates. As material spirals into the black hole's accretion disk, it heats up to millions of degrees, unleashing torrents of radiation and powerful jets that can outshine an entire galaxy. But here's the twist: that incredible energy doesn't just light up the cosmos, it can also sterilize it. The intense radiation and winds from a quasar blast through the surrounding galaxy, heating interstellar gas to such extreme temperatures that it can no longer cool and collapse to form new stars. It's like a cosmic feedback loop. The black hole's feast starves the galaxy of its future. This process, called quasar feedback, might explain why some massive galaxies stop forming stars and become cosmic graveyards. Without cool gas, star formation grinds to a halt, leaving behind aging populations of stars with no new generations to replace them. Observations of distant galaxies show this exact scenario playing out. In one striking case, astronomers found a galaxy where the central quasar's jets had drilled through surrounding gas clouds, creating vast bubbles of scorching plasma. Where those bubbles expanded, star formation simply stopped. The galaxy's fate was sealed not by external forces, but by the very engine at its core. Yet this destructive power isn't one-sided. The same black holes that can stifle star formation also seem to regulate their galaxy's growth. Computer simulations reveal something extraordinary. Without these periodic outbursts, galaxies would grow too large, too fast, forming stars at unsustainable rates that would burn through their fuel reserves in cosmic nanoseconds. The black hole acts like a cosmic thermostat, stepping in when things get too hot. Its outbursts, though violent, prevent the galaxy from exhausting itself too soon. This delicate balance suggests something profound, that black holes and galaxies evolve together, locked in a dance of creation and destruction. The same gravity that draws gas toward the black hole also funnels material into star-forming regions until the black hole's own appetite disrupts the flow. It's a cycle as old as the universe itself, one that's etched into the very structure of galaxies we see today. The largest galaxies with the most massive black holes often show the clearest signs of this feedback, their star-forming days long behind them. But the story doesn't end there. Sometimes the black hole's influence is more direct. In merging galaxies, the collision funnels vast amounts of gas toward the center, igniting not just a frenzy of star formation, but also awakening the dormant black hole. The resulting quasar can then blast away the galaxy's remaining gas, shutting down star formation entirely. It's a cosmic paradox. The very mergers that build galaxies can also trigger the mechanism that ends their growth. What's truly mind-bending is how precise this feedback appears to be. Across billions of years and countless galaxies, the mass of a galaxy's central black hole closely correlates with the properties of its surrounding stars. This suggests an intimate, almost conversational relationship, as if the galaxy and its black hole are constantly negotiating, balancing growth against restraint. The implications stretch beyond individual galaxies. This feedback mechanism might explain why the universe isn't drowning in stars. Without black holes to temper their growth, galaxies could have turned all their gas into stars long ago, leaving the universe dark and lifeless. Instead, we live in a cosmos where black holes, those ultimate destroyers, paradoxically help maintain the conditions for galaxies and life to endure. So the next time you hear about a distant quasar blazing across the cosmos, remember, you're witnessing not just a black hole's feast, but a moment of cosmic regulation. These titanic eruptions aren't just spectacles, they're the universe's way of keeping its grandest structures in check. Spiral galaxies like the Milky Way present one of the most mesmerizing sights in the cosmos, their elegant arms swirling outward like delicate brushstrokes across a celestial canvas. But here's the cosmic twist. Those iconic spiral arms aren't rigid structures at all. They're dynamic patterns, fleeting illusions created by the movement of stars and gas, like traffic jams in a galactic highway. This revelation comes from density wave theory, a groundbreaking idea that fundamentally changed how we understand galaxy structure. Imagine a busy freeway during rush hour. Cars don't stay locked in the same traffic jam forever. They enter, slow down, and eventually exit the congestion. Spiral arms operate the same way. stars and gas clouds orbit the galactic center at different speeds, bunching up in regions where gravity creates a wave of higher density. As they pass through these crowded zones, star formation ignites, lighting up the spiral pattern with brilliant young stars. But the individual stars don't stay put, they drift through the arms like cars navigating a bottleneck, while the pattern itself persists like a slow-moving ripple in a pond. This explains why spiral arms appear so vivid despite the chaos of galactic motion. The brightest, bluest stars, those massive, short-lived giants, form in the densest parts of the wave, illuminating the arms before burning out. Older stars, having passed through the pattern long ago, scatter across the galaxy's disk, fading into the background. Meanwhile, new stars continuously replenish the spiral's glow, creating the illusion of a permanent structure. It's as if the galaxy is a conveyor belt of starlight, with the arms acting as glowing checkpoints rather than fixed trails. The proof lies in meticulous observations of stellar motions. By tracking individual stars, astronomers have caught them in the act, entering, traversing, and exiting spiral arms over millions of years. Computer simulations reinforce this, showing how density waves self-perpetuate, with gravity constantly reshaping the pattern as the galaxy rotates. Some spiral arms even fade and reappear over time, their longevity dependent on the delicate balance between gravitational forces and the galaxy's rotation. This process isn't just a quirk of physics, it has profound implications for galactic evolution. Spiral arms act as cosmic nurseries, compressing gas clouds to trigger star birth. Without these density waves, galaxies might lack the vibrant structure that defines them. Yet the arms aren't eternal. Collisions, mergers, or even internal instabilities can erase them, transforming spiral galaxies into smoother, more featureless ellipticals over billions of years. So the next time you see an image of a spiral galaxy, remember, you're witnessing a grand, slow-motion dance, a fleeting arrangement of starlight that persists not because the stars stay, but because the pattern endures. The universe's most breathtaking shapes are often its most ephemeral, a reminder that even in the vastness of space, beauty is always in motion. The Milky Way seems like a tranquil cosmic island when we gaze at its glowing band across the night sky. But beneath that serene facade lies evidence of a tumultuous past, one written in the scattered remains of galaxies it consumed long ago. Recent discoveries from the Gaia Space Observatory have peeled back the layers of our galaxy's history like a cosmic archaeologist brushing dust off ancient artifacts. What they've uncovered is astonishing. The Milky Way didn't grow peacefully over time. It gorged itself on smaller galaxies in violent mergers, each collision leaving indelible scars in its halo of stars. One of the most dramatic events, now called the Kraken merger, stands out as a defining moment in our galaxy's adolescence. About 11 billion years ago, when the Milky Way was just a fraction of its current size, a massive dwarf galaxy, 4 times heavier than any other it had absorbed, slammed into it. The impact was catastrophic. The intruder's stars were torn apart by tidal forces. Their orbits scrambled until they blended into the Milky Way's halo, forming a ghostly, diffuse cloud that still lingers today. Tracking these stars was like reconstructing a crime scene. Astronomers used Gaia's precise measurements of stellar positions and velocities to trace their motions backward through time, revealing their shared origin in this primordial collision. But the Kraken wasn't alone. Our galaxy's halo is a graveyard of galactic remnants, each with its own distinct chemical signature. Some stars move in tight, looping orbits, betraying their origins in smaller, swallowed galaxies. Others cluster in streams that stretch across thousands of light years, like ribbons of stardust marking the paths of long-vanished systems. One of the most famous is the Gaia-Enceladus merger, a collision that occurred around 10 billion years ago and deposited millions of stars into the Milky Way's outer reaches. These stars are metal-poor compared to the galaxy's native population, a telltale sign they formed early, before generations of supernova enriched the cosmos with heavier elements. What's remarkable is how these mergers shaped the Milky Way's evolution. The Kraken's impact, for instance, didn't just add stars, it likely triggered a frenzy of star formation, its gravitational disturbance compressing gas clouds until they ignited into brilliant new suns. Some of the oldest stars in our galaxy's thick disk may owe their existence to this violent encounter. Even the Milky Way's majestic spiral structure might have been influenced by these ancient mergers, their gravitational echoes subtly steering the motions of stars and gas over eons. The Gaia mission has revolutionized our understanding of these events by mapping nearly 2 billion stars with unprecedented precision. Its data acts like a galactic time machine, allowing scientists to identify stellar families based on their motions and compositions. One group might move in unison, a relic of a dwarf galaxy shredded billions of years ago. Another might orbit backward, a sign of a particularly chaotic merger. Together, they form a cosmic palimpsest, layers of history written in starlight, waiting to be decoded. These collisions weren't just destructive, they were creative. Each merger brought fresh gas and stars, fueling the Milky Way's growth and diversifying its stellar population. Without them, our galaxy might have remained a small, unremarkable collection of stars. Instead, it became the grand spiral we know today, its past etched into the very fabric of its halo. The next time you look up at the Milky Way, remember, you're not just seeing stars, you're gazing at the fossilized remains of galaxies that once were, their stories woven into ours. Galaxies, much like living creatures, have life cycles. Some blaze into existence with bursts of star formation, while others fade into quiet obscurity. Take the red and dead ellipticals, colossal, smooth galaxies devoid of the vibrant blue hues of young stars, their gas supplies long exhausted. These cosmic retirees drifted through eons, their star-forming factories shut down, leaving behind only aging red stars slowly burning out. For decades, astronomers assumed their fate was sealed. Once a galaxy stopped forming stars, it was game over, but the universe loves a good plot twist. Enter the Phoenix Cluster, a galaxy cluster so named for its central galaxy's astonishing rebirth. At its heart lies a supermassive black hole, typical for such giants, but unlike others, this one isn't stifling star formation. Instead, it's allowing cooling flows, a rare phenomenon where gas chilling at the cluster's core rains back onto the galaxy, reigniting star birth. Imagine a dormant volcano suddenly erupting with fresh lava, or a withered tree sprouting new leaves after centuries. That's the Phoenix Cluster's central galaxy, defying expectations by producing around 740 new stars per year, a staggering rate compared to the Milky Way's modest 1 or 2. How does this cosmic resurrection happen? The answer lies in a delicate balance between heating and cooling. In most galaxy clusters, supermassive black holes pump energy into their surroundings, preventing gas from cooling enough to form stars. But in the Phoenix Cluster, something's different. The black hole's outbursts aren't powerful enough to stop the cooling entirely. Gas condenses into dense clouds, collapsing under gravity's pull and sparking a stellar renaissance. It's as if the galaxy stumbled upon a hidden reset button, turning back the clock on its own evolution. This discovery shattered assumptions about galactic death. Instead of a one-way journey toward stagnation, some galaxies might cycle between active and dormant phases, their fates hanging on the interplay between black holes and cooling gas. Even more intriguing, the Phoenix Cluster isn't alone. A handful of other rejuvenating galaxies have been spotted, their star formation rekindled by similar mechanisms. It raises a tantalizing question: could our Milky Way, billions of years from now, experience its own revival? The implications ripple beyond single galaxies. These cycles of starbirth and quenching sculpt the large-scale structure of the universe, influencing how galaxy clusters evolve over time. They remind us that cosmic processes are rarely as final as they seem. What appears dead might just be waiting for the right conditions to bloom again. So the next time you hear about a dead galaxy, remember, in the cosmos, endings are often just pauses in a much longer story, stretching across unimaginable distances like slender rivers of darkness. Cosmic filaments weave the largest structures in the universe, threads of dark matter and gas so vast they could connect galaxies like beads on a string. The most spectacular of these, nicknamed the cosmic snake, spans an astonishing 500 million light-years, a gravity-bound highway channeling fresh gas into galaxies hungrily forming stars at its nodes. This discovery didn't come from spotting the filament itself. These structures are too faint to see directly, but from their ghostly imprint on space-time. When light from distant galaxies passes near these massive filaments, their immense gravity bends the light's path, warping background galaxies into eerie arcs and multiple images. Astronomers call this gravitational lensing, nature's magnifying glass revealing the hidden scaffolding of the cosmos. The cosmic snake isn't just a curiosity, it's a lifeline. Simulations suggest that filaments like this one funnel cold gas into galaxies at rates up to 10 times faster than random accretion, fueling explosive star formation. Picture it like a cosmic irrigation system where filaments act as aqueducts delivering water to thirsty fields. In this case, the water is hydrogen gas, the raw material for new stars, and the fields are young galaxies growing at the intersections of these vast filaments. The snake's structure is particularly striking. Its tendrils branch like lightning, frozen in mid-strike, each fork terminating in a galaxy brimming with newborn stars. Some of these galaxies appear warped into multiple images by the filament's gravity, giving astronomers an unprecedented view of their interiors. What makes this discovery revolutionary isn't just the filament's scale, but its role in galactic growth. Before the cosmic snake's observation, astronomers debated whether galaxies grew primarily through mergers or steady gas accretion. Now, we see direct evidence for a hybrid model. Filaments deliver gas efficiently while also guiding smaller galaxies toward mergers. The snake's galaxies are caught in a cosmic tug-of-war. Gravity pulls them along the filament toward eventual collisions, even as the same structure feeds them fresh fuel. This dual mechanism explains why some galaxies in dense environments grow so rapidly, their star formation rates dwarfing isolated galaxies floating in voids. The filament structure holds even more secrets. Detailed spectroscopy reveals its gas isn't uniformly distributed. Clumps and knots along its length suggest turbulence from ancient galactic winds or shock waves from long-dead quasars. These irregularities act like dams in a river, momentarily pooling gas before it spills onward to feed waiting galaxies. Some segments of the snake glow faintly in X-rays, betraying the presence of shock-heated gas where filaments intersect, like cosmic traffic jams in the flow of matter. Perhaps most astonishing is the snake's longevity. Unlike the brief, violent mergers that reshape galaxies in an instant, filaments operate on timescales spanning billions of years. Galaxies embedded in them grow steadily, their star formation regulated by the filament's relentless delivery of fresh gas. This slow, sustained growth might explain why some galaxies avoid burning out too quickly. Their fuel supply isn't sporadic but constant, like a well-tended fire. The cosmic snake isn't alone. Surveys of the distant universe reveal an entire web of similar filaments, each channeling matter along gravity's invisible contours. Together, they form the cosmic web's backbone, a network so immense that if we could see it all, the universe would resemble froth on an ocean wave, with galaxies clinging to the intersections of bubbles. The snake is just one thread in this tapestry, but its discovery proves what theorists long suspected. The universe builds its grandest structures one filament at a time, weaving galaxies into the dark fabric of space. Deep in the cosmic wilderness, galaxies sometimes go berserk, transforming into monstrous stellar factories that churn out thousands of stars per year in a frenzy that defies all expectations. Meet the starburst galaxies, cosmic overachievers where star formation isn't just active, it's downright apocalyptic. Take the baby boom galaxy, a record holder caught birthing stars at a rate of 4,000 per year. To put that in perspective, our Milky Way manages just 1 or 2 stars annually, making these starburst galaxies the equivalent of a wildfire next to a candle. What could possibly trigger such extreme behavior? The answer lies in galactic collisions, where 2 gas-rich galaxies smash together in slow motion. When their interstellar gas clouds collide, shock waves ripple through them, compressing the gas to densities hundreds of times greater than normal. It's like squeezing a sponge until it gushes, except here, the sponge is light years wide, and instead of water, it's spewing newborn stars. The sheer violence of these mergers explains why starbursts are so intense, but here's the puzzle. According to our best models, these galaxies should burn through their entire gas supply in just a few million years, a blink in cosmic time. Yet we see starbursts lasting 10 times longer, suggesting they're somehow cheating the system. Part of the secret might lie in cold gas streams, invisible rivers of hydrogen flowing in from intergalactic space, constantly replenishing the galaxy's fuel reserves. Another clue comes from the baby boom galaxy's infrared glow, so intense it outshines its visible light. That radiation comes from dust grains heated by countless young stars, and the dust itself plays a surprising role. It acts like a cosmic pressure cooker, trapping radiation that would otherwise blow gas away, allowing star formation to continue far longer than physics predicts. But the real shocker, some starbursts aren't triggered by mergers at all. Galaxies like Messier 82 erupt into frenzied star formation simply by passing too close to a massive neighbor, their gas squeezed by gravitational tides without a direct collision. This means starbursts aren't just cosmic accidents, they're an integral part of galactic evolution, sculpting the universe's structure in ways we're only beginning to understand. Their extreme conditions even offer a glimpse into the early universe, when all galaxies might have formed stars at similarly frantic rates. These stellar firestorms don't last forever, though. Eventually, the combined winds and radiation from all those new stars will blast away the remaining gas, and the galaxy will settle into quiet middle age. But not before seeding the cosmos with generations of stars, planets, and perhaps even life. The starburst phase might be brief, but its legacy lasts billions of years. Among the cosmic menagerie of galaxies, some defy every expectation, so faint they're nearly invisible, yet so massive their gravity betrays an astonishing secret. Take Dragonfly 44, a ghostly giant lurking in the Coma cluster. At first glance, it resembles a wisp of interstellar smoke, its stars scattered so thinly that the galaxy emits just 1% of the Milky Way's light. But here's the enigma. Despite its feeble glow, Dragonfly 44 moves like a heavyweight. Measurements of its star's velocities reveal a gravitational grip so strong it must contain nearly as much mass as our galaxy. Where is all that missing matter? The answer might rewrite our understanding of dark matter itself. These elusive objects, called ultra-diffuse galaxies, shouldn't exist according to conventional models. Their stars are so sparsely distributed that without a colossal halo of dark matter binding them together, they'd have evaporated into the void eons ago. Yet Dragonfly 44's dark matter isn't just present, it's packed into an unprecedented ratio, making up 99.9% of the galaxy's mass. That's like finding a balloon that weighs as much as a freight train. How could such a fragile structure hold so much hidden weight? Theories range from failed galactic embryo systems that started forming stars but stalled, to the splattered remains of ancient collisions, their stars scattered but their dark matter left intact. The mystery deepens when we compare them to other galactic oddballs. Some ultra-diffuse galaxies, like those in the NGC 1052 group, are dark matter deficient, flouting expectations entirely. Others, like the newly discovered fluffy galaxies in the Perseus cluster, contain almost no dark matter at all, challenging the notion that it's essential for galactic survival. This bipolar behavior has astronomers scrambling. Are these galaxies born different, or did something strip them down over time? One clue comes from their environments. Many ultra-diffuse galaxies orbit near massive galaxy clusters, where tidal forces could have ripped away their gas and stars while leaving their dark matter untouched, like cosmic sandblasters stripping paint from a metal frame. The implications ripple far beyond these ghostly galaxies. If dark matter can cluster so densely in objects like Dragonfly 44, it might mean our models of how dark matter behaves are incomplete. Perhaps it interacts with itself in ways we haven't accounted for, or maybe these galaxies are signposts to an entirely new class of dark matter structures. Telescopes like the James Webb Space Telescope are now targeting these enigmas, peeling back their faint light to study their star populations for clues. Every flicker of starlight from these cosmic phantoms carries a message, one that might force us to rethink the invisible scaffolding of the universe itself. Every star in a galaxy carries a hidden record of its birth, a chemical fingerprint revealing not just its age, but the very conditions of the cosmic environment that forged it. Like tree rings chronicling centuries of growth, the distribution of elements within a galaxy's stars maps its evolutionary journey in stunning detail. Astronomers call this galactic archaeology, and the tool they use is metallicity, the abundance of elements heavier than hydrogen and helium. These heavier elements, forged in stellar cores and scattered by supernova, act as cosmic breadcrumbs, tracing a galaxy's growth spurts, mergers, and even its darkest secrets. Take the Milky Way's disk, for example. Stars near the galactic center are typically metal-rich, packed with elements like iron and silicon. Venture outward, though, and metallicity drops steadily, a gradient echoing our galaxy's inside-out formation. Early on, gas concentrated in the dense core birthed generations of stars quickly, each wave of supernova seeding the next with heavier elements. As the galaxy expanded, newer stars formed from progressively cleaner gas, resulting in today's declining metallicity gradient. It's a pattern seen in spirals across the universe, but deviations from this rule reveal dramatic twists in a galaxy's story. Some galaxies, like Andromeda, show flatter gradients hinting at a violent past where mergers stirred their stellar populations like spoons in coffee. Others, like the ancient relic galaxy NGC 1277, have virtually no gradient at all, their stars uniformly metal-poor. This suggests they formed most of their stars in one furious burst early on, then shut down, preserving a snapshot of the young universe's chemistry. Even more intriguing are galaxies with inverted gradients, where outer stars are richer in metals, evidence of gas stolen from neighboring galaxies or late-stage accretion from metal-enriched cosmic filaments. The key to unlocking these histories lies in spectroscopy, where astronomers dissect starlight into rainbows of color. Dark absorption lines in these spectra act like barcodes, each corresponding to specific elements. By measuring their depth and position, scientists can calculate a star's composition with astonishing precision. Modern surveys like the Sloan Digital Sky Survey have automated this process, analyzing millions of stars to build chemical maps of entire galaxies. These maps reveal substructures invisible to traditional imaging streams of stars with matching metallicity, betraying their origin in long-digested dwarf galaxies or distinct populations tracing past epochs of star formation. One striking discovery involves alpha elements like oxygen and magnesium, produced mainly in massive stars that die young. Their ratio to iron, which trickles out more slowly from smaller stars, acts as a cosmic clock. High alpha-to-ion ratios signal rapid star formation, where generations of massive stars lived and died in quick succession. Low ratios suggest a more leisurely pace, with time for smaller stars to contribute ion between bursts. In the Milky Way's halo, some stars show alpha-rich compositions, relics from an era when our galaxy was assembling itself in violent, gas-rich mergers. But metallicity doesn't just record a galaxy's past, it influences its future. Heavy elements cool gas more efficiently, enabling denser star-forming clouds. This creates a feedback loop where metal-rich galaxies keep forming stars longer, while metal-poor ones stall. Some dwarf galaxies, like those in the local group, appear stuck in this trap, their low metallicity gas unable to collapse effectively, leaving them frozen in time. Meanwhile, galaxies like our own owe their continued star formation to that slow, steady enrichment over billions of years. The ultimate goal, to reconstruct entire galactic genomes, chemical timelines detailing every merger, burst, and quenching event. With upcoming telescopes like the Extremely Large Telescope poised to analyze stars in distant galaxies, we're on the verge of reading these cosmic histories not just in our Milky Way but across the universe. Each star's elements are verses in an epic poem, and we're only beginning to learn the language. Deep in the direction of the constellations Centaurus and Hydra, something invisible exerts an irresistible gravitational tug on our Milky Way and thousands of other galaxies, an unseen force dragging us toward it at 14 million miles per hour. Astronomers call this cosmic mystery the Great Attractor, and its true nature remains one of the most tantalizing puzzles in modern astrophysics. What could possibly command such control over the motions of entire galaxies? The answer lies buried under a thick veil of interstellar dust, where our own galaxy's disk blocks direct observation, turning this region into a celestial blind spot. The first clues emerged in the 1970s when astronomers mapping the universe's large-scale motions noticed something bizarre. Instead of drifting apart evenly with the universe's expansion, galaxies in our local supercluster, including the Milky Way, were all streaming toward the same patch of sky. The magnitude of this motion defied explanation. To account for such a colossal pull, there had to be an unprecedented concentration of mass lurking in that direction, roughly equivalent to tens of thousands of Milky Ways packed into a region 600 million light-years across. Yet when telescopes scanned the area, they found nothing matching that staggering scale. Further studies revealed the Great Attractor isn't a single monstrous object, but likely the heart of the Laniakea supercluster, an immense web of galaxies stretching 500 million light-years, with our Milky Way residing on its fringes. At its core lies the Norma cluster, a dense knot of galaxies and hot gas whose combined gravity acts as the anchor for this vast cosmic watershed. Imagine a mountain range where rivers flow inexorably downhill. In this analogy, Laniakea is the mountain, and galaxies like ours are the rivers, sliding along invisible gravitational slopes toward the supercluster's center. But here's where the plot thickens. Even Laniakea's immense gravity can't fully explain the Great Attractor's pull. Peering beyond it, astronomers uncovered something even more massive: the Shapley supercluster, a gargantuan assembly of galaxy clusters lying 800 million light-years away. Shapley's gravity appears to be tugging on Laniakea itself, creating a nested hierarchy of cosmic attraction. This suggests the Great Attractor phenomenon isn't caused by one structure, but by the combined pull of multiple superclusters in a vast, interconnected flow of matter stretching across the observable universe. What makes this discovery so groundbreaking is its challenge to our understanding of cosmic evolution. These flows imply that the universe isn't just expanding uniformly, it's also seething with vast, slow-moving currents of galaxies responding to gravitational imbalances from the Big Bang's primordial density variations. The Great Attractor is merely our local manifestation of this universal pattern, a signpost pointing to how deeply structure is woven into the fabric of space-time. Efforts to map this hidden realm continue with innovative tools. X-ray telescopes pierce the Milky Way's dust, revealing galaxy clusters glowing with million-degree gas. Radio surveys trace the motions of hydrogen clouds, while infrared observations spot stars forming in obscured galaxies. Each new dataset brings us closer to unraveling the full extent of this cosmic confluence. And as we peel back the layers, we're forced to confront a humbling truth. Even our galaxy, vast as it is just a speck caught in a gravitational current far grander than we ever imagined. So the next time you look toward Centaurus, know this: every star in that direction is racing toward an unseen destiny, swept up in a river of galaxies flowing toward mysteries we're only beginning to glimpse. The universe isn't just expanding, it's moving, dancing to the tune of gravity's invisible hand. And somewhere in that darkness, the great attractor waits, its full story still untold. When galaxies collide, they don't just rearrange themselves, they spawn entirely new cosmic entities in the chaos. The antennae galaxies, locked in a slow-motion dance of destruction, offer one of the most spectacular examples of this phenomenon. As these two spirals tear through each other, their mutual gravitational forces don't merely stretch their familiar shapes into long, antenna-like streams of stars. They also fling massive clumps of gas and dust out into intergalactic space. But here's where the real magic happens. Those ejected clouds, rich with star-forming material, sometimes collapse under their own gravity to form brand new galaxies. These celestial newborns, called tidal dwarf galaxies, defy conventional galactic wisdom in fascinating ways. Unlike typical galaxies, which form within massive halos of dark matter, tidal dwarfs are born from pure baryonic matter, the ordinary atoms that make up stars, planets, and us. Observations of systems like NGC 702-9 reveal tidal dwarfs glowing with young blue star clusters, their chemical compositions matching the spiral arms they were ripped from rather than the primordial gas of traditional galaxies. They're essentially cosmic orphans carrying the DNA of their parent galaxies in their stellar populations. The creation process resembles a cosmic slingshot effect. During galactic collisions, tidal forces can accelerate gas clouds to incredible speeds fast enough to escape their parent galaxy's grasp, but not so fast that they disperse entirely. As these clouds travel through intergalactic space, their internal gravity overcomes the expansive energy of the collision, causing them to contract. Shock waves from the merger compress the gas further, triggering intense bursts of star formation. What emerges is a self-contained island of stars, often just 1,000th the mass of the Milky Way, yet shining brightly with the energy of its newborn suns. One of the most surprising aspects of tidal dwarfs is their durability. Without dark matter's gravitational scaffolding, astronomers initially doubted these galaxies could survive long. Yet studies of systems like the Tadpole Galaxy's tidal tail show some tidal dwarfs persisting for billions of years, their stars orbiting a common center of mass despite the lack of invisible glue. Their continued existence provides crucial insights into how gravity binds visible matter alone, a rare opportunity to study galactic-scale dynamics without dark matter's complicating effects. These peculiar galaxies also serve as cosmic Rosetta Stones, helping astronomers decode the histories of galactic collisions. By analyzing tidal dwarfs' motions and compositions, researchers can reconstruct the precise angles and speeds of ancient mergers. Some even contain mixed populations of stars from both parent galaxies, acting as living records of these violent encounters. And in a beautiful twist of cosmic irony, the same forces that tear galaxies apart can thus create fresh stellar communities, reminding us that in the universe, destruction and creation are often two sides of the same coin. Future observations with next-generation telescopes promise to reveal even more about these dark matter-free oddities. Some theories suggest they might form planetary systems differently than traditional galaxies, with altered ratios of heavy elements affecting planet formation. Others speculate that tidal dwarfs could be more common than we realize, potentially accounting for some of the ultra-diffuse galaxies recently discovered in galaxy clusters. Whatever secrets they still hold, one thing is certain: these celestial underdogs prove that even in the most violent cosmic events, new beginnings can emerge from the wreckage. Computer simulations of the cosmos have a startling prediction. Our Milky Way should be surrounded by thousands of dwarf galaxies, tiny cosmic satellites orbiting like bees around a hive. Yet when astronomers peer into the night sky, they count barely dozens. This glaring mismatch, known as the missing satellite problem, has haunted astrophysicists for decades, revealing gaps in our understanding of galaxy formation and the very nature of dark matter. The roots of this cosmic discrepancy lie in the lambda cold dark matter model, our leading framework for how structures evolve in the universe. According to these simulations, dark matter should clump into countless small halos early in cosmic history, each one massive enough to attract gas and ignite star formation. The math suggests our galaxy's gravitational pull should have captured thousands of these dwarf galaxies over billions of years. But reality paints a different picture. Only about 60 confirmed satellites circle the Milky Way, with similarly sparse numbers around Andromeda. Where are all the missing dwarfs? One compelling solution involves the very nature of star formation in these tiny galaxies. While dark matter halos may indeed be plentiful, many could simply be too small or gas-poor to light up with stars. Ultra-faint dwarfs like Segway 1, barely visible against the cosmic backdrop, hint that some halos did form stars, but at such meager rates they're nearly undetectable. Others might have been strangled before they could shine, their gas stripped away by the Milky Way's tidal forces or by blistering ultraviolet radiation in the early universe, leaving behind dark galaxies of pure dark matter. Another twist comes from the properties of dark matter itself. If it's warmer or more interactive than current models assume, it could suppress the formation of the smallest halos, naturally explaining the observed satellite count. Alternatively, feedback from supernova and young stars in these dwarfs might have blown out their gas prematurely, starving them of the fuel needed to form visible stars. The puzzle grows richer with recent discoveries. Projects like the Dark Energy Survey have uncovered new ultra-faint dwarfs hiding in plain sight, so dim they blend into the Milky Way's glow until sophisticated algorithms tease them from the noise. Each new detection edges us closer to reconciling theory with observation, yet even collectively, they barely dent the thousands still missing. Perhaps the most intriguing possibility is that the missing satellites aren't missing at all, or just transformed. Galactic tides stretch and shred dwarf galaxies over time, smearing their stars into faint streams like those found wrapping around the Milky Way. These stellar rivers, once distinct galaxies, now weave through our halo like cosmic graffiti, their origins erased by time. Others might have plunged into the galactic disk long ago, their stars assimilated into the Milky Way's bulk, making our galaxy's outer regions a graveyard of failed dwarfs. As telescopes grow more sensitive, the census of these elusive satellites continues to rise. But whether the solution lies in better observations, revised dark matter physics, or some undiscovered quirk of star formation, one thing is certain: the missing satellites problem isn't just about counting galaxies. It's a profound test of our entire understanding of cosmic structure, reminding us that even our best simulations are only shadows of the universe's true complexity. Galaxies aren't static islands of stars, they're dynamic ecosystems where matter circulates in vast, slow-motion cycles that would dwarf any weather system on Earth. Imagine a cosmic water cycle, but instead of rain and evaporation, it's driven by the explosive deaths of stars. When a massive star reaches the end of its life and detonates as a supernova, the blast doesn't just light up the galaxy, it hurls enormous quantities of gas outward at millions of miles per hour, creating expanding bubbles that rise like hot air balloons above the galactic disk. These aren't fleeting phenomena. These structures, called galactic fountains, can tower tens of thousands of light years into the halo, carrying enough material to build entire generations of new stars. What goes up must come down even in space. As these gas clouds ascend, they gradually cool over hundreds of millions of years, condensing into dense filaments that gravity eventually pulls back toward the disk. Picture molten wax dripping down the side of a candle, except each droplet contains enough gas to form millions of stars. Observations of galaxies like the Milky Way reveal this process in action, with towering arcs of gas fluorescing in ultraviolet light as they fall back, a phenomenon astronomers poetically call cooling rains. In the spiral galaxy NGC 6891, the Hubble Space Telescope even captured this recycled gas glowing blue as it plunges back into star-forming regions, literally feeding the next wave of stellar birth. This recycling system solves a cosmic mystery. Without a way to replenish its gas supply, a galaxy would exhaust its star-forming fuel in just a few billion years. Galactic fountains extend that timeline dramatically, keeping galaxies alive far longer than simple models predict. The numbers are staggering. Our Milky Way likely ejects and recycles about 1 solar mass worth of gas every year through this process. Over cosmic timescales, that adds up to enough material to build entire star clusters from scratch. But the fountain effect isn't just about quantity, it's about quality too. As the gas cycles through these loops, it undergoes a transformative purification process. Supernova enrich the ejected material with heavy elements forged in stellar cores, while the long journey through the halo allows lighter elements like hydrogen to recombine into molecules. By the time this gas returns, it's chemically primed for efficient star formation, like cosmic compost enriching a galactic garden. Some theories even suggest our Sun may have formed from such recycled material, its planets inheriting atoms that once floated far above the galactic plane. The most spectacular fountains occur in starburst galaxies, where frenzied star formation leads to correspondingly violent supernova activity. In galaxies like Messier 82, these outflows become so powerful they drive gas clear out of the galaxy entirely, creating intergalactic pollution that can eventually seed neighboring systems. Yet even in quieter spirals like our own, the fountain effect shapes galactic evolution in profound ways. Computer simulations show how returning gas tends to rain down preferentially along spiral arms, reinforcing their structure and perpetuating the galaxy's iconic shape. Perhaps the most astonishing implication is temporal. A single fountain cycle from ejection to return can take longer than Earth's entire existence as a habitable planet. The gas now falling back onto the Milky Way's disk may have been blasted upward before multicellular life arose on our world, completing a journey that spans geological epochs. And just as these ancient outflows now nurture new stars, today's supernova are launching material that will one day sustain galaxies far in the future, a cosmic cycle of death and rebirth written across the light years. Lurking at the very edge of the observable universe sits GNZ 11, a faint smudge of light that holds an extraordinary title, the oldest galaxy humanity has ever glimpsed. This cosmic relic shines from an astonishing 13.4 billion years in the past, a time when the universe was a mere 400 million years old, still shaking off the afterglow of creation. To put that into perspective, when GNZ 11's light began its journey, the Milky Way wouldn't exist for another 8 billion years. What makes this discovery even more remarkable is how it defies expectations. This ancient galaxy shouldn't be so bright, so mature, yet there it glows, a cosmic toddler already bustling with star formation. The Hubble Space Telescope first spotted GNZ 11 in 2016, but it took the James Webb Space Telescope's infrared vision to reveal its true significance. Where Hubble saw only a dim speck, JWST detected the telltale fingerprints of heavy elements like oxygen and carbon elements that shouldn't have existed so soon after the Big Bang. These metals, forged in the hearts of early stars and scattered by supernova, suggest GNZ11 experienced multiple generations of star formation in just a few 100 million years. That's like finding a fully formed city in what should be an empty wilderness, forcing astronomers to rethink how quickly galaxies could assemble in the universe's chaotic infancy. But GNZ11's reign as the oldest known galaxy may soon end. JWST's unprecedented sensitivity is peeling back the cosmic curtains even further, uncovering candidates from earlier epochs, including one tantalizing detection from just 225 million years after the Big Bang. These potential record breakers appear as infinitesimal red dots in JWST images, their light stretched beyond visible wavelengths by the universe's expansion. Each one pushes the boundary of how soon stars and galaxies could ignite after the cosmic dawn. Some theories suggest the very first galaxies might have formed in halos of exotic population 3, stars, hypothetical giants made purely of hydrogen and helium that burned hot and died young, seeding the cosmos with the first heavy elements. What's truly mind-bending is how these ancient galaxies differ from modern ones. GNZ11 packs all its luminosity into a region just 1% the size of the Milky Way, yet it forms stars 20 times faster. This frenzied pace hints at a universe where gravity worked overtime, compressing gas into dense knots that ignited stars in furious bursts. JWST spectral analysis reveals another surprise. These early galaxies often appear lumpy and irregular, lacking the majestic spiral arms or smooth ellipses we associate with their modern counterparts. They're cosmic experiments testing what shapes galaxies can take when the rules of the universe are still being written. The hunt for these primordial galaxies isn't just about breaking records. Each one acts as a time capsule, preserving clues about the epoch of reionization when the first starlight burned away the hydrogen fog that filled the early universe. GNZ11's intense radiation likely helped clear this cosmic haze in its neighborhood, creating bubbles of transparency that allowed light to travel freely for the first time. JWST's growing catalog of ultra-distant galaxies is mapping how this process unfolded across space and time, revealing whether reionization happened in sudden flashes or a gradual brightening. As astronomers push closer to the Big Bang itself, they're confronting profound questions. How did gravity sculpt galaxies so quickly after inflation? Could dark matter's peculiar properties in the early universe have accelerated their growth? And might there be galaxies even older than JWST can see, their light forever stretched beyond detectability by the universe's relentless expansion? For now, GNZ11 stands as a beacon from the cosmic frontier, a reminder that the universe's childhood was far more dynamic and creative than we ever imagined. Galaxies aren't always victims of cosmic circumstance. Sometimes they orchestrate their own demise from within. Take the case of massive galaxies that mysteriously quench, shutting down their own star formation like a factory closing its production lines. Unlike galaxies stripped of gas by external forces, these cosmic burnouts face an internal revolt, a rebellion led by the very stars and black holes that once fueled their brilliance. At the heart of this self-destruction lies a phenomenon called AGN feedback, where a galaxy's central supermassive black hole turns from a passive occupant into an active saboteur. When gas funnels toward the black hole, it doesn't just vanish quietly, it's compressed and heated to millions of degrees, creating an accretion disk that blasts out radiation and jets of plasma at near light speed. These outbursts act like cosmic blowtorches, heating surrounding gas clouds until they're too energetic to collapse and form new stars. In galaxy cluster MS0735, astronomers witnessed this process in stunning detail. jets from the central black hole had carved enormous cavities in the cluster's hot gas, leaving vast regions where star formation was impossible. The black hole wasn't just feeding, it was sterilizing its own galaxy. But black holes don't act alone. Massive stars contribute to this self-quenching through their own violent life cycles. When these stars die as supernova, their explosions don't just enrich the galaxy with heavy elements, they also drive powerful stellar winds that sweep up surrounding gas like cosmic bulldozers. In galaxies with intense star formation, like the starburst galaxy M82, these combined winds create fountain-like outflows visible across thousands of light years. The gas isn't just displaced, it's often heated or accelerated enough to escape the galaxy entirely, robbing it of future star-forming fuel. The quenching process creates a stark divide in galactic demographics. On one side, blue spiral galaxies like the Milky Way continue forming stars at a modest pace, their gas reservoirs replenished by occasional mergers or cosmic filaments. On the other, red and dead ellipticals like those in the centers of galaxy clusters sit idle, their remaining stars aging toward reddish hues without new generations to replace them. What determines which path a galaxy takes? Surprisingly, it often comes down to mass. Massive galaxies have deeper gravitational wells, making it harder for gas to escape, but that same gravity also feeds their central black holes more efficiently, leading to stronger AGN feedback. It's a cosmic catch-22. The conditions that allow a galaxy to grow large also activate the mechanisms that will eventually shut it down. Computer simulations show this feedback cycle in action. Black holes initially stoke star formation by compressing gas clouds, only to later overheat the system like a runaway thermostat. The timing is critical: too early and the galaxy remains small; too late and it becomes a red giant. Only through this delicate balance does the universe maintain its diverse population of galaxies. Evidence for self-quenching isn't just theoretical. Observations of post-starburst galaxies reveal populations where star formation stopped abruptly 1 billion years ago, leaving an excess of middle-aged stars but no newborn. Their spectra tell the story. Chemical signatures show they once formed stars vigorously before something cut off their gas supply. Crucially, these galaxies often show signs of past AGN activity but no major mergers, pointing to internal rather than external causes. The implications stretch beyond individual galaxies. This self-regulating process helps explain why the universe isn't blanketed entirely in stars, why some regions remain fertile while others become cosmic deserts. Without quenching, massive galaxies might have turned all their gas into stars eons ago, leaving the modern universe dark and lifeless. Instead, we live in a cosmos where galaxies, like living organisms, contain the seeds of both their growth and their limitation. A reminder that even the grandest structures must eventually slow, not because they've run out of resources, but because they've used them too well. Surrounded by the glittering expanse of the cosmos, our Milky Way sits in a strangely quiet neighborhood, a cosmic backwater perched on the edge of a staggering emptiness called the local void. This vast, bubble-like region stretches over 150 million light-years and contains almost nothing. No galaxies, no star clusters, just an eerie, near-perfect vacuum. While most of the universe resembles a bustling metropolis of galaxies clumped along filaments, we find ourselves in the celestial equivalent of rural farmland, with wide open spaces separating us from the bright lights of the Virgo cluster and other dense galactic gatherings. This isolation isn't just a curiosity, it's a puzzle. The standard model of cosmic structure predicts that matter should be distributed more evenly, with galaxies filling space like foam in a bubble bath. Yet the local void defies expectations, its near emptiness challenging our understanding of how the universe organizes itself. One theory suggests it's a relic of the early universe's uneven density, a region where dark matter's gravitational scaffolding failed to gather enough gas to form galaxies. Another possibility is that the void grew over time as larger structures around it sucked away matter like cosmic sponges, leaving behind this expansive nothingness. Our position on the void's edge gives astronomers a unique laboratory. From here, we can study how the void's gravity, or lack thereof, affects the motion of nearby galaxies. The Milky Way, along with our local group neighbors like Andromeda, isn't standing still. We're all being pulled toward denser regions, particularly the Shapley supercluster, the most massive concentration of matter in our cosmic vicinity. But the local void exerts its own subtle push, its emptiness creating a kind of negative gravity that repels galaxies away from it. This cosmic tug of war shapes the large-scale flow of galaxies in ways we're only beginning to map. Ironically, this isolation may have been crucial for life's emergence. In denser regions, galaxies collide more frequently, their turbulent environments bombarding planets with lethal radiation and gravitational disruptions. Our quiet corner, by contrast, has allowed the Milky Way to evolve relatively undisturbed for billions of years, a stable home where solar systems like ours could form and endure. The void's emptiness, then, isn't just a cosmic oddity. It might be the very reason we're here to ponder it. Future telescopes, like the Nancy Grace Roman Space Telescope, aim to probe the void's boundaries with unprecedented precision, searching for any faint dwarf galaxies that might lurk in its depths. Each new observation helps refine our models of cosmic structure, revealing how emptiness shapes the universe as profoundly as the glittering galaxies do. So the next time you gaze at the night sky, remember, the darkness between the stars isn't just empty space, it's part of a grand, invisible architecture, and our place within it is anything but random. The first galaxies in the cosmos looked nothing like the majestic spirals and smooth ellipticals we see today. Instead, they resembled cosmic toddlers, messy, disorganized, and full of chaotic energy. Observations from the Hubble and James Webb Space Telescopes reveal these ancient systems as clumpy, irregular blobs, their stars scattered like handfuls of glitter tossed across the darkness. Without the elegant symmetry of modern galaxies, these primordial structures blazed with frenetic star formation, their shapes constantly distorted by internal turbulence and frequent collisions. The difference between then and now isn't just aesthetic, it's a record of billions of years of galactic maturation, a story written in the slow dance of gravity, gas, and time. What transformed these cosmic rough drafts into the polished masterpieces we see today? The answer lies in two relentless processes: mergers and gas depletion. Early galaxies grew by cannibalizing their neighbors, their gravitational pulls drawing smaller systems into violent embraces. Each collision stirred the galactic pot, smoothing out irregularities and redistributing stars into more orderly configurations. Picture a snow globe shaken by a child. At first, the flakes scatter wildly, but as the turbulence fades, they settle into a harmonious drift. Similarly, mergers provided the energy to reshape galaxies, their gravitational interactions acting like cosmic sculptors chiseling chaos into symmetry. But mergers alone don't explain the full metamorphosis. The early universe was awash in gas, the raw fuel for star formation, and young galaxies burned through it recklessly. Over time, as galaxies exhausted their reserves and supernova blasted leftover gas into intergalactic space, star formation slowed. Without constant bursts of new stars to light up their clumpy formations, galaxies grew calmer, their structures stabilizing. Spiral arms emerged as density waves organized remaining gas into graceful patterns, while elliptical galaxies formed when major mergers thoroughly scrambled stellar orbits, erasing all traces of their disordered past. The transition wasn't uniform. Some galaxies, like those in dense clusters, evolved quickly, their gas stripped away by harsh environments, leaving them red and dead by cosmic middle age. Others, like the Milky Way, took a more measured approach, conserving gas and maintaining steady star formation to preserve their spiral beauty. even now, the process continues, dwarf galaxies merging with larger ones, streams of gas raining back onto galactic disks, and the occasional violent collision reshaping destinies. The most striking evidence of this evolution comes from galactic archaeology studying the ages and compositions of stars within modern galaxies. In the Milky Way's halo, ancient stars move in chaotic orbits, relics of the disorderly past, while younger disk stars follow nearly circular paths, a sign of the galaxy's increasing stability over time. Similarly, elliptical galaxies are dominated by old red stars, their brief, fiery youths long behind them, while spiral disks still sparkle with blue star-forming regions. This galactic aging process has profound implications for the universe's future. As galaxies continue to consume their gas and merge, the era of grand spirals will fade, leaving behind predominantly smooth, red ellipticals in a darker, quieter cosmos. Yet even in that distant future, the legacy of those early, chaotic builders will endure, their stardust now woven into generations of stars, planets, and perhaps even life. A reminder that structure emerges from turbulence and beauty from the slow, patient work of time. Though Wolf Disk shouldn't exist, this colossal galaxy, spinning gracefully just 1.5 billion years after the Big Bang, defies everything we thought we knew about galactic infancy. With a diameter rivaling the Milky Way's and a well-formed spiral structure, it looks like it had billions of years to mature. Yet it appeared when the universe was barely 10% of its current age. According to standard models, galaxies this size and complexity simply couldn't form so quickly. They'd need time to accumulate gas, settle into disks, and develop orderly rotation. Yet there it sits in telescope images, a cosmic rebel challenging our timeline of cosmic evolution. What makes the Wolf Disk so baffling is its sheer normalcy. Unlike the chaotic, clumpy galaxies we typically see from this epoch, it displays the elegant symmetry of a much older system. Observations from the Atacama Large Millimeter Array reveal cold gas swirling in a stable disk at speeds over 270 kilometers per second, clear evidence of advanced structural development. This isn't some starbursting oddball surviving on cosmic chaos. It's a refined, well-ordered galaxy behaving like it's middle-aged while the rest of the universe is still in diapers. Several theories attempt to explain these impossible giants. One radical suggestion posits that the early universe's dark matter halos were far denser than we thought, providing gravitational wells deep enough to rapidly collect and organize vast amounts of gas. Another idea points to cold accretion, streams of chilled hydrogen flowing along dark matter filaments directly into galactic centers, bypassing the hot, turbulent phases that normally slow galactic growth. There's even speculation that the first supermassive black holes acted as cosmic anchors, their immense gravity helping stabilize gas clouds into disks faster than previously believed possible. The Wolf Disk isn't alone in its defiance. Galaxy G09091, another early universe behemoth, contains as many stars as our Milky Way despite appearing just 3 billion years after the Big Bang. Even more extreme, Galaxy HLF-LS3 boasts a stellar mass equivalent to 800 billion suns, quadruple the Milky Way's, at a time when most galaxies were still struggling to reach 1% of that size. Each of these cosmic anomalies shares a common trait. They appear fully formed in an era when, according to our models, they should still be amorphous blobs of gas. These discoveries force us to reconsider fundamental aspects of galactic growth. Perhaps mergers played a larger role in the early universe than we realized, with pre-existing building blocks colliding to rapidly assemble mature galaxies. Or maybe star formation operated with unprecedented efficiency in the primordial cosmos, converting nearly all available gas into stars at breakneck speeds. Some astronomers even suggest tweaking the very nature of dark matter itself, making it slightly warmer or more interactive to explain how structures could form so quickly. The implications ripple far beyond these individual galaxies. If massive, well-ordered systems were common in the early universe, our entire timeline for cosmic evolution may need revision. The epoch of reionization, when the first starlight burned away the cosmic fog, might have started earlier than we thought, driven by these unexpectedly advanced galaxies. Their existence could also help explain where today's supermassive black holes came from, providing the massive seeds needed to grow billion solar mass monsters in relatively short order. As telescopes like JWST peer deeper into the cosmic dawn, they're uncovering more of these rule-breaking giants, each one challenging our understanding of how the universe builds its grandest structures. The Wolf disk and its ilk aren't just astronomical curiosities, they're cosmic provocateurs, forcing us to question whether we've fundamentally misunderstood the universe's childhood. In their majestic, impossible spiral arms, we may find the clues to rewriting galactic history itself. In the early universe, the first stars didn't just light up the cosmos, they fundamentally altered its chemistry in ways that would shape galactic evolution for billions of years. These massive, short-lived behemoths blazed with ultraviolet radiation so intense it acted like a cosmic sandblaster, stripping electrons from hydrogen atoms in a process called reionization. While this cleared the fog that once filled space, allowing light to travel freely, it also created an unexpected side effect: galactic light pollution. The same radiation that made the universe transparent also heated vast reservoirs of intergalactic gas, making it too energetic to collapse into new galaxies. Imagine trying to build a snowman during a heat wave. That's what later galaxies faced in this newly ionized environment. Before reionization, pristine hydrogen gas could cool efficiently, clumping together under gravity's pull to form stars and galaxies with ease. But once those first stars and galaxies flooded the cosmos with UV light, the remaining gas became too hot and agitated to settle down. The universe's baby boom of galaxy formation slowed dramatically, not because it ran out of raw materials, but because those materials had become too unruly to use. Regions that missed the early rush of galaxy growth found themselves at a permanent disadvantage, their gas heated beyond usefulness like a scattered puzzle that could never be reassembled. This phenomenon explains one of the universe's great disparities: why galaxies in dense clusters tend to be older and redder, while those in isolation are younger and bluer. Early forming galaxies emerged when the cosmic gas supply was still cold and plentiful, allowing them to grow rapidly. Latecomers trying to assemble in already ionized voids struggled to gather enough cool gas to ignite significant star formation. Telescopes like Hubble have captured this divide in stunning detail, showing clusters of ancient galaxies surrounded by vast bubbles of ionized gas, fossilized evidence of the radiation that stifled further growth. The most extreme example lies in the Lyman alpha blobs, enormous clouds of hydrogen glowing faintly from reionization's aftereffects. These structures, some spanning hundreds of thousands of light years, contain enough gas to form entire galaxies, yet they remain diffuse and unproductive, their atoms too energized by ancient starlight to coalesce. It's as if the first stars not only illuminated the universe but also left behind a lingering barrier, a cosmic keep-out sign written in ultraviolet. Yet even this light pollution had a silver lining. By regulating galaxy formation, it prevented smaller systems from hoarding gas inefficiently, ensuring that later galaxies, including our Milky Way, would inherit a universe where resources were concentrated enough to build stable, long-lived structures. The same radiation that suppressed growth in voids also funneled gas along filaments toward denser regions, creating the conditions for grand spirals and mature ellipticals. In this way, the first stars didn't just change the universe's composition, they set the stage for everything that followed, their light echoing through time as both a creator and a limit. The Milky Way's serene spiral arms and shimmering disk hide a dramatic future, one written in the relentless pull of gravity. 4.5 billion years from now, our galaxy will collide with its nearest neighbor, Andromeda, in a slow-motion cosmic ballet that will reshape both forever. NASA simulations paint a breathtaking sequence. First, the two galaxies will approach each other at nearly 250,000 miles per hour, their mutual gravity stretching long tendrils of stars into a bridge between them. Then, over hundreds of millions of years, they'll swing past each other in a gravitational embrace, their spiral structures torn apart by tidal forces before finally merging into a single, colossal elliptical galaxy, dubbed Milky Way by astronomers. This collision won't be the violent smash-up it sounds like. The vast distances between stars mean direct stellar impacts are vanishingly rare. You could count the number of stars that might physically collide on one hand. Instead, the merger will play out like two flocks of birds swirling together, their individual motions chaotic but their collective shape gradually blending. Andromeda's slightly larger mass means it will dominate the final product, its central black hole eventually merging with the Milky Ways to form a supermassive binary before coalescing into a single, even more monstrous gravitational anchor. What's truly astonishing is how much we already know about this event. By tracking Andromeda's motion with precision measurements from the Hubble Space Telescope, astronomers have confirmed the inevitability of the collision. The galaxy's mutual gravitational attraction overrides the universe's expansion in our local neighborhood, pulling them together despite the cosmic tide pushing everything else apart. Advanced simulations factor in every variable from dark matter halos to gas dynamics, rendering the merger in stunning detail. One simulation even shows our solar system's possible fate. There's a 50% chance we'll be flung outward into Milky Way's extended halo, and a small but real possibility we might get ejected entirely, becoming intergalactic wanderers. The aftermath will be spectacular but strangely serene. As the galaxies merge, their gas clouds will collide, triggering fireworks of new star formation, though these bursts will pale in comparison to the frenzied starbursts of their youth. Over time, the merged galaxy stars will settle into randomized orbits, erasing all traces of the original spirals and leaving behind a smooth, football-shaped ellipse. The night sky from any surviving planets will transform. Utterly gone will be the Milky Way's familiar band, replaced by a scattered haze of stars and the glowing remnants of the collision's final act. This future merger isn't unique, it's the universe's standard playbook for galactic evolution. But for us, it's personal, a reminder that even our grand galaxy is just a temporary arrangement of stars, destined to blend into something new. The cosmic timescales might dwarf human existence, but they etch a humbling truth: everything in the universe, even the mightiest structures, is in motion, forever drawn together by gravity's patient, unyielding hand. Dark matter was supposed to be the invisible glue holding galaxies together until astronomers found the unthinkable, a galaxy seemingly without any. NGC 1052DF2 shocked the scientific community when measurements revealed its stars moved at speeds explainable by visible matter alone, defying decades of assumptions about how galaxies work. This cosmic oddball, floating in near silhouette against distant galaxy clusters, shouldn't exist according to conventional models. Yet there it was, its pale glow betraying no trace of dark matter's gravitational influence. A ghost ship sailing through space without the hidden ballast that supposedly keeps all galaxies afloat. The discovery sent ripples through astrophysics because it cuts to the heart of our understanding of cosmic structure. For 40 years, the prevailing lambda-cold dark matter model treated dark matter as essential scaffolding, collapsing first into halos that then attracted gas to form galaxies. NGC 1052DF2's apparent lack of dark matter suggests galaxies might form through entirely different pathways. Some theorists propose it's a tidal dwarf galaxy, born from gas stripped during a violent galactic collision and thus composed purely of ordinary matter. Others speculate it could be a failed galaxy that somehow lost its dark matter halo, perhaps through interactions with neighboring massive galaxies. Controversy erupted when alternate measurements suggested NGC 1052DF2 might be closer than initially thought, which would mean its stars move slower, potentially allowing for some dark matter after all. But then came NGC 1052DF4, another bizarre object in the same group showing similarly perplexing star motions, followed by a handful of other dark matter-deficient candidates. Each new find deepened the mystery, forcing astronomers to confront uncomfortable questions. Could there be multiple ways to build a galaxy, or are we misinterpreting the evidence entirely? The implications are staggering. If dark matter-free galaxies are real, they provide a unique laboratory to study gravity's behavior on galactic scales without dark matter's complicating effects. Their existence might also explain anomalies in the universe's expansion rate or hint at exotic physics involving dark matter particles interacting in ways we haven't accounted for. Alternatively, they could be cosmic illusions, galaxies where dark matter is present but unseen because it's distributed differently than models predict, or where extreme environments have masked its gravitational signature. Future observations with telescopes like the James Webb Space Telescope aim to settle the debate by precisely measuring these galaxies' distances and stellar compositions. Whatever the outcome, these enigmatic systems have already accomplished something remarkable. They've reminded us that the universe always has surprises in reserve, and that even our most cherished theories must bow to the evidence. In that way, whether NGC 1052DF2 truly lacks dark matter or not, it's already reshaped our cosmic perspective. Peering back to the cosmic dawn, the James Webb Space Telescope has captured something extraordinary: pristine gas clouds so ancient they might be caught in the act of forming the universe's very first galaxies. These aren't fully fledged galaxies yet, but their embryonic glow offers a glimpse into a time when the cosmos was just learning to build its grand structures. One such discovery, a filament of cold hydrogen stretching across the early universe, glows faintly in JWST infrared gaze. It's a cosmic umbilical cord, feeding raw material into dense knots where gravity's pull is strong enough to birth entire galactic systems. What makes these clouds so special is their untouched composition. Unlike modern gas clouds laced with heavy elements from generations of dead stars, these primordial pockets contain almost nothing but hydrogen and helium, the pure ingredients of the Big Bang itself. Their lack of heavier elements suggests they're among the universe's first construction sites, where gas first began coalescing under dark matter's invisible guidance. JWST spectroscopic eyes reveal their internal dynamics in stunning detail: turbulent motions hinting at gravitational instability, subtle temperature variations marking regions where collapse might already be underway. The most tantalizing targets are the so-called dark galaxies, clouds massive enough to form stars, yet mysteriously devoid of any stellar light. These shadowy giants, detected only through their absorption of background quasar light, could represent a missing link in galactic evolution. They're cosmic blank canvases waiting for the first spark of nuclear fusion to ignite within them. One particularly massive cloud, dubbed the CR7 filament after an earlier Hubble discovery, now appears in JWST vision as a sprawling river of gas, its denser nodes glowing with the telltale signatures of gravitational heating, a sign that collapse into protogalaxies may have already begun. What's revolutionary about these observations isn't just their age, but their scale. Traditional models assumed the first galaxies formed from small, isolated gas clouds, but JWST data suggests a more interconnected picture. Vast networks of gas filaments crisscross the early universe like cosmic highways, funneling material into growing hubs. Some filaments stretch for hundreds of thousands of light years, their gravitational pull orchestrating the birth of multiple protogalaxies simultaneously. It's a top-down approach to galaxy formation that challenges earlier bottom-up theories, showing how the universe might have built its largest structures faster and more efficiently than we ever imagined. The implications ripple across astrophysics. If these filaments are indeed the progenitors of modern galaxy clusters, they could explain how supermassive black holes grew so quickly in the early universe. Their dense central nodes would provide ideal nurseries for black hole seeds, which could then feast on the abundant surrounding gas. Similarly, their pristine chemistry offers clues about the elusive population Roman III stars, hypothetical first-generation stars thought to be hundreds of times more massive than our Sun. JWST hunt for their distinctive helium-rich spectra in these clouds could finally confirm their existence or force us to rethink stellar formation's earliest chapters. Yet for all their significance, these gas clouds are fleeting cosmic moments. Within a few 100 million years, a blink in universal time, they'll either collapse into true galaxies or be shredded by the growing radiation from the first stars. JWST unparalleled sensitivity lets us catch them in this transitional state, frozen between the simplicity of the early universe and the complexity to come. Each observation is a time capsule from an era when the cosmos was still assembling its rulebook, a reminder that even the mightiest galaxies began as nothing more than whispers in the dark. At the heart of the ravenous galaxy J2157 lurks a cosmic monstrosity so voracious it defies belief, a supermassive black hole tipping the scales at 34 billion times the mass of our Sun, consuming the equivalent of an entire star's worth of material every single day. This isn't just the fastest-growing black hole we've ever discovered, it's a gravitational abyss reshaping everything around it, blazing with the energy of 1,000 galaxies as it tears apart gas clouds, stars, and even other black holes with insatiable hunger. What makes J2157 so extraordinary isn't just its staggering appetite, it's the sheer improbability of its existence. Black holes this massive shouldn't have had enough time to form so early in the universe's history, yet there it sits, blazing brightly when the cosmos was barely 1.5 billion years old. To put that in perspective, this black hole grew to 20 times the mass of Sagittarius A, the Milky Way's central black hole, in less than 10% of the time our galaxy has existed. It's like finding a fully grown blue whale in a toddler's swimming pool, an object so out of scale with its environment that it forces us to rethink everything about how cosmic giants are born. The secret to J2157's rapid growth might lie in its cosmic surroundings. This galaxy exists in an unusually dense region of the early universe, where dark matter filaments funneled vast amounts of gas directly into its core. Imagine a city built at the confluence of a dozen rivers. Now replace the rivers with currents of primordial hydrogen, and the city with a black hole's event horizon. The gas doesn't just fall in smoothly, it spirals into the abyss at relativistic speeds, colliding with itself in shockwaves that heat it to millions of degrees. This superheated maelstrom glows so brightly that J2157 outshines the combined light of every star in its host galaxy, making it visible across 12 billion light-years of space. Yet even this feeding frenzy has limits. Black holes can't grow infinitely. Their own radiation creates powerful winds that eventually push away the gas they crave. J2157's extreme luminosity suggests it's teetering on this edge, its outward radiation pressure nearly strong enough to cut off its own food supply. That tension creates a bizarre cosmic balancing act. The more it eats, the harder it becomes to keep eating, like a fire so hot it burns its own fuel source too quickly. This self-regulation might explain why we don't see even larger black holes. There comes a point where their hunger becomes their own undoing. The discovery of J2157 has profound implications for our understanding of galactic evolution. Its existence hints at a population of direct collapse black holes, primordial giants that formed directly from collapsing gas clouds in the early universe, bypassing the usual stellar mass black hole stage entirely. These cosmic titans could have served as seeds for the supermassive black holes we see today, solving the long-standing puzzle of how such massive objects appeared so quickly after the Big Bang. But J2157 isn't just a relic, it's a window into the fate of all galaxies. Left unchecked, its central black hole could eventually unleash a quasar so powerful it sterilizes the entire galaxy, shutting down star formation for good. That future might be inevitable after all. Every giant was once a devourer, and in the dark heart of J2157, we're witnessing the raw power that shapes the cosmos. Buried in the faint static between radio stations lies one of the most astonishing relics of the cosmos, a whisper of radiation from the universe's first starlight, captured not by optical telescopes but by antennas listening to the void. The EDGE's experiment in the remote Australian outback made history when it detected this elusive signal, a dip in radio waves at 78 MHz, corresponding to the moment when ultraviolet radiation from the earliest galaxies stirred the primordial hydrogen fog filling the young universe. This subtle fluctuation, less than 1% the strength of background noise, acts like a cosmic echo, revealing how infant galaxies transformed the cosmos in their fiery birth. The physics behind this echo is deceptively simple yet profound. Before stars existed, hydrogen atoms floated in a cold, dark sea, their electrons and protons spinning in perfect sync. When the first galaxies ignited, their ultraviolet light excited these atoms, causing them to absorb background radiation at a specific wavelength like tuning forks, resonating to a particular musical note. As the universe expanded, that absorbed radiation stretched into longer radio waves, preserving a fingerprint of that pivotal transition we can detect today. The EDGE's team likened it to hearing the distant echo of a shout across a canyon, except the shout happened 13 billion years ago, and the canyon is the entire observable universe. What makes this detection so revolutionary is its direct window into the cosmic dawn, the poorly understood era when the first galaxies burned away the hydrogen fog. Traditional telescopes glimpse this epoch only indirectly through ancient galaxies at the edge of visibility, but radio observations like EDGE's bypass those limitations by sensing the hydrogen itself, which acted as a vast cosmic microphone recording the first stellar fireworks. The signal's depth suggests the early universe was far colder than predicted, possibly due to interactions between dark matter and hydrogen, a tantalizing hint at physics beyond our current models. Follow-up projects like the Square Kilometre Array aim to map this hydrogen echo in 3 dimensions, revealing where the first galaxies clustered and how quickly they illuminated the cosmos. Already, the signal hints at surprises. The reionization process may have started later but progressed faster than simulations suggested, with galaxies flooding the universe with light in a relative flash. These findings don't just tweak our cosmic timeline, they reshape our understanding of how quickly tiny fluctuations in the infant universe snowballed into the glittering cities of galaxies we see today. Yet for all its insights, the EDGE's detection remains controversial. Independent teams have struggled to confirm it, and some argue terrestrial interference could mimic the signal. But if validated, this ghostly radio whisper will stand as one of cosmology's crowning achievements, proof that even in the silent static between stations, the universe's origin story is still broadcasting, waiting for us to tune in. The universe doesn't just build galaxies, it weaves them into structures of unimaginable scale, stretching the very definition of what we thought possible. Enter the Boss Great Wall, a galactic megastructure so vast it makes our local superclusters look like neighborhood cul-de-sacs. This staggering filament of galaxies spans over 1 billion light-years, a spider's silk threaded with tens of thousands of galaxies, each one a glittering island in the cosmic web. To grasp its scale, imagine traveling at light speed from one end to the other. You'd spend longer crossing this single structure than multicellular life has existed on Earth. Discovered in 2016 by the Baryon Oscillation Spectroscopic Survey, This titanic wall is more than just a record breaker, it's a stress test for cosmology itself. According to standard models of cosmic structure formation, nothing this colossal should exist. The early universe's density fluctuations simply shouldn't have allowed matter to cluster on such preposterous scales. Yet there it hangs in the constellation sextants, its galaxies moving in eerie synchrony, bound by gravity's invisible threads. The wall's sheer existence forces us to reconsider fundamental assumptions. Either our understanding of dark matter's role in structure formation is incomplete, or the universe played a cosmic trick, arranging matter in patterns far grander than we ever predicted. What's truly mind-bending is how the Boss Great Wall behaves as a single entity. Unlike random galaxy clusters, its components share coherent motion, flowing along the filament like cars on a freeway. This suggests the structure isn't just a chance alignment, it's a unified gravitational system, with dark matter's pull orchestrating the motion of galaxies across billion light-year distances. Some sections show galaxies moving in opposite directions, hinting at colossal collision zones where entire superclusters may eventually merge. Others contain eerie voids, regions almost devoid of galaxies, as if the wall were a cosmic sponge with holes punched through it. Mapping this leviathan required innovative techniques. Astronomers didn't just count galaxies, they measured their redshifts with exquisite precision, using baryon acoustic oscillations, frozen sound waves from the early universe as cosmic yardsticks. These subtle fingerprints, imprinted when the cosmos was just 400,000 years old, stretch across the Boss Great Wall like grid lines on a map, revealing how its galaxies trace primordial density variations. The resulting three-dimensional map shows the wall's intricate substructure, dense knots where multiple filaments intersect, feeding superclusters with thousands of Milky Way-sized galaxies, while thinner tendrils connect these hubs like galactic interstate highways. But here's the twist: the Boss Great Wall might not even hold its title for long. New surveys hint at even larger structures lurking in deeper redshift data, including potential walls spanning 1.4 billion light-years. Each discovery pushes the boundaries of what we consider a coherent cosmic structure, blurring the line between individual galaxies and the universe's large-scale architecture. These titanic formations aren't just scientific curiosities, they're cosmic mirrors, reflecting back our incomplete understanding of gravity, dark matter, and the universe's deepest organizing principles. What's most humbling is realizing our place within this tapestry. The Boss Great Wall lies about 5 billion light-years away, meaning we're seeing it as it existed before Earth even formed. While we marvel at its scale from afar, somewhere within its filamentary embrace, countless stars may host planets where other beings gaze back at our corner of the cosmos, equally awestruck by the universe's boundless capacity for grandeur. Among the endless variety of galaxies, some cosmic oddballs refuse to fit neatly into our classification system's flaunting shapes, so bizarre they challenge everything we thought we knew about galactic structure. At the top of this celestial freak show sits Hoag's object, a galaxy so perfectly ringed it looks like someone dropped a cosmic smoke ring into the void. Discovered in 1950 by astronomer Art Hoag, this enigmatic structure features a golden core of ancient stars encircled by a flawless blue ring of newborn suns, with a yawning gap of near-total darkness in between. No spiral arms, no messy distortions, just an eerie, symmetrical halo floating in space like a celestial bullseye. For decades, astronomers scratched their heads over how such a pristine ring could form. The usual suspects, galactic collisions, seemed unlikely, as there's no visible debris or neighboring galaxies that could have caused such a neat impact. One theory suggests Hoag's object is a rare example of a resonance ring, where density waves from a past interaction organized gas into this flawless circle over billions of years. Another idea proposes an extreme version of bar instability, where a central bar of stars dissolved, flinging material outward into this perfect ring. But the truth is, no model fully explains its symmetrical perfection, making it one of the universe's most elegant mysteries. Then there's the so-called space triangle, a bizarre three-armed structure born from a chaotic three-way galactic collision in the constellation Lynx. Unlike the neat rings of Hoag's object, this cosmic demolition derby produced a jagged, wedge-shaped galaxy with stars strewn in every direction. Hubble images reveal the aftermath in stunning detail. 3 spiral galaxies, each once orderly, now locked in a gravitational tug of war that's twisted them into a single triangular monstrosity. The collision triggered starbursts so intense they're visible across 300 million light-years, with newborn star clusters blazing along the wreckage like sparks from a grinding wheel. What makes these oddballs so valuable isn't just their strangeness, it's what they reveal about the flexibility of galactic physics. Hoag's object proves galaxies can self-organize into forms we barely understand, while the space triangle shows how chaotic mergers can birth entirely new galactic species. They're cosmic boundary pushers, demonstrating that the universe's creativity far outstrips our tidy classification schemes. Even more intriguing, these misfits might be more common than we thought. Recent surveys suggest up to 1% of galaxies defy standard categories, lurking in plain sight until sharper telescopes reveal their true forms. The lesson is clear: for every rule we devise about how galaxies should look, the cosmos whispers back with exceptions. Whether it's polar ring galaxies with halos perpendicular to their disks, or jellyfish galaxies trailing star-forming tentacles from ram pressure stripping, these outliers remind us that the universe prefers diversity over order. In their defiance, they reveal the hidden possibilities of galactic evolution, showing us that even in the vastness of space, true originality still exists. Imagine a cosmos grown old, a universe where the last stars have flickered out, galaxies have faded into darkness, and even black holes, those indomitable monsters, have dissolved into faint wisps of radiation. This isn't the apocalyptic vision of an exploding sun or colliding galaxies. It's a far quieter, more inevitable fate, one that unfolds over timescales so vast they dwarf even the age of the universe so far. We're talking about the ultimate destiny of galaxies, not in billions but trillions of years, when the universe itself becomes a graveyard of scattered stardust. The first stage of this cosmic twilight begins with the gradual shutdown of star formation. As galaxies exhaust their reservoirs of interstellar gas, burned up in stellar furnaces or blown away by supernova and black hole winds, the birth rate of new stars plummets. Spiral arms fade as their gleaming young stars die out, leaving behind only dim red dwarfs, the universe's most miserly and long-lived stars. These faint embers will continue glowing for perhaps 10 trillion years, far longer than the current age of the universe, but even they aren't eternal. One by one, they too will sputter out, leaving galaxies cloaked in darkness, their once vibrant disks now populated by cooling stellar corpses, white dwarfs, neutron stars, and the occasional black hole. But the story doesn't end there. Over even longer timescales, gravity's relentless pull begins to unravel the galaxies themselves. Stars, though sparse, still interact gravitationally, their orbits gradually destabilizing. Some will be flung out into intergalactic space, while others will spiral inward, merging or being devoured by the supermassive black holes at galactic centers. The elegant spiral structures we know today will dissolve into amorphous, diffuse clouds of stars drifting further apart as the universe's expansion accelerates. In time, even galaxy clusters once tightly bound by gravity will disperse, their member galaxies pulled apart by dark energy's inexorable push. The final chapter belongs to black holes. For eons, they will be the last sentinels of galactic structure, anchoring their surroundings with unimaginable gravity, but even they are not forever. Through a process called Hawking radiation, black holes slowly lose mass, emitting faint particles until, over unimaginable timescales, they evaporate entirely. A supermassive black hole like Sagittarius A, weighing millions of suns, might take 10 to the power of 100 years to vanish, a number so large it defies comprehension. When the last black hole finally winks out of existence, the universe will enter the so-called dark era, a cold, empty expanse where nothing remains but scattered subatomic particles and the faint echo of radiation, stretched to undetectable wavelengths by the universe's endless expansion. Yet in this seemingly bleak future, there's a strange kind of poetry. Every atom that once burned in stars, every planet that harbored life, every galaxy that blazed with light, all of it traces back to the same cosmic beginnings. Even in the darkness, the universe carries the memory of what it once was, a testament to the fleeting but extraordinary era when matter briefly organized itself into something complex enough to wonder about its own existence. The fate of galaxies isn't just an end. It's the closing stanza of an epic written in starlight. From the quantum ripples that seeded galaxy formation to the dark matter scaffolding shaping the cosmic web, every discovery we've explored shatters our assumptions about the universe and our place within it. Consider that the atoms in your body were forged in stars birthed from galactic collisions. That invisible dark matter's grip determines whether a galaxy spins or falls apart. And that supermassive black holes act as cosmic regulators, capable of both igniting and extinguishing star formation with their violent outbursts. These aren't just distant curiosities, they're threads in the story that led to planets, life, and conscious beings able to ponder the cosmos. The Wolf Disk's impossible maturity and J2157's ravenous black hole reveal how much we've underestimated the early universe's creativity. Ghostly ultra-diffuse galaxies and dark matter-deficient oddballs prove nature crafts cosmic specimens beyond our textbooks. Even galactic cannibalism, the Milky Way's hidden graveyard of consumed dwarfs, shows destruction and rebirth are woven into existence itself. Perhaps most humbling is the realization that galaxies evolve and perish on timescales dwarfing human history, their fates dictated by forces we're only beginning to decode. Carl Sagan's pale blue dot perspective takes on new depth against these discoveries. That iconic image of Earth as a speck in the cosmic dark wasn't just about scale. It revealed how all human struggles, triumphs, and borders vanish when framed against the universe's grand narrative. Every war fought, every work of art created, every civilization risen and fallen occurred on a mote of dust adrift in a galaxy that itself is one in hundreds of billions, fleeting against the canvas of deep time. Yet here we are, the universe's way of understanding itself, tracing our lineage back to those first stars whose deaths made our atoms, to those galactic collisions that forged our solar system's cradle. This cosmic perspective isn't meant to diminish human significance, but to redefine it. We aren't just inhabitants of space, we're its awakening. The same laws that sculpt galaxies also govern the neurons firing in your brain as you grasp these ideas. So while we may be small in the grand scheme, we're profoundly rare a universe's attempt to witness its own majesty. The next time you gaze at the night sky, remember, you're not just looking at distant lights. You're seeing home, history, and possibility, a tapestry still being woven with our tiny